Log on, tune in, find out. Another good idea from Cambridge.
So it's my pleasure to introduce Joel Kamnitzer from Toronto, who will tell us about MV polytopes and components of quiver varieties.
Thanks very much for the invitation to speak and for the invitation to come visit this institute, join the program. It's been a very nice visit so far. So I'd like to tell you about some work that I was doing with Pierre Baumann. And we actually started this work last year when we were both visiting MSRI as part of the program there that some people I know here were also at. And but it's a little bit been on hiatus. But in a couple of weeks I'll be visiting him in Strasbourg, so hopefully we'll finish up this project. So the motivation is the study of special bases for representations of Lie algebras. So let me sort of give you start with this kind of schematic. So two such special bases are Lustig's canonical basis and another such special basis is the called Mirkovich-Vilonen basis. And both these bases are defined using some geometry. Well, Lustig's canonical basis doesn't necessarily need to be defined using this geometry, but let's say it's defined using some geometry, namely geometry, in this case, geometry of quiver varieties. And in this case, the Mirkovich-Vilonen basis is defined using the geometry of affine Grassmannians. It's kind of a mystery that there should be two different bases defined by some geometric constructions, and yet these geometric constructions appear to be quite different, and it's not clear how these two things are related. So kind of an open problem is to understand the relation. So one way to start is to build a kind of bridge between them, at least on a combinatorial level. So that's what I'm going to talk about today, and the bridge is built using the theory of MV Mirkovich-Vilonen polytopes. So these polytopes were originally defined starting from these Mirkovich-Vilonen bases. So when I write such and such basis, really I'm thinking such and such subvarieties of the affine Grassmannian or certain subvarieties of quiver varieties, which this side I'll tell you much more about soon. So the connection here was originally established, well, the definition of these guys from these guys was originally established by Jared Anderson in his thesis and later further studied by myself. And on the other hand, there was also a connection between this Lustig canonical basis and Mirkovich-Vilonen polytopes, a kind of, in some sense, indirect connection using the work of Lustig and of Berenstein and Levinsky. So the goal, what I'm going to tell you about now, is an attempt to make a kind of more direct connection between MV polytopes and the varieties that come up in Lustig's canonical basis, such that this connection looks more similar to this connection. So try to make these two pictures look more similar. Okay, so let me get to some specifics. So we'll start with G, which will be a simple Lie algebra over C. So I'm going to start, in the beginning I'll start by, on this side, with the geometry of the quiver varieties. So we'll take Q to be the associated quiver, by which I just mean the Dynkin diagram with an orientation, so something like this, if our Lie algebra was SL4. Then Q bar will be the doubled quiver. So I just double all my edges. And then I form the pre-projective algebra. I'll call it A of Q. So which is you take the path algebra of the doubled quiver, quotient by the ideal generated by the element C, where C is the sum over all alpha arrows in the original quiver, a star minus a star, sorry, alpha alpha star minus alpha star alpha, where alpha means that the arrow in the original quiver, now thought of as an arrow in the doubled quiver, and alpha star means the arrow pointing backwards in the doubled quiver. So path algebra means I just take all paths in my Q bar. So I'll make this definition less mysterious in a second. So to make it less mysterious, so we're going to be studying modules for this pre-projective algebra. So let me explain how to think of a module for a pre-projective algebra. So an A Q module V is the same thing as the following two pieces of data: a direct sum decomposition of V into vector spaces labeled by I. So you get these, starting with the algebra, you get these VI by hitting your module with the path that starts at the ith vertex and goes nowhere. Here I is the set of vertices. My quiver. And the second piece of data that goes into the module is for each arrow in the original quiver, alpha, an arrow in the original quiver, we have a linear map. J, so alpha goes from I to J in the original quiver, linear. And another one which goes backwards. Okay? And to be a module, the condition of quotienting by this ideal generated by this C amounts to the following fact: that for each I, the sum over all arrows alpha starting at I, if you look at the ways to make your linear map that goes out and then back, this should be equal to the sum over ways to go in and over ways to go, well, also out and then back, but using now different arrows. Okay. So in this example, a module for the pre-projective algebra associated with this quiver would be the same thing as a vector space for each vertex, linear maps for each arrow. The sum, say here, so here if we did this thing at this vertex, we just get that this composition was 0. At this vertex, we would get that this composition equaled this composition. And at this vertex, we just get that this composition was 0. So let's let lambda pos be the positive sums of positive roots for our Lie algebra, subset of the weight lattice of our Lie algebra. And then we can associate to each module the dimension of V, which will be the sum, by definition, the sum of the dimensions of VI's times alpha i's. Alpha i's are our simple roots. So that's the dimension. Now, for beta in this lambda pos, the lambda pos is just the same thing as the non-negative integer linear combinations of the alphas. So if you have such a beta, namely beta is a non-negative linear combination of the alphas, then defines x of beta to be the variety of A of Q modules on fixed vector spaces vi equals c to the ni. In other words, we'll just fix these vector spaces vi to be just c to the ni, and then consider the variety of all module structures we can put on this fixed vector spaces, which means, so this will be a subvariety of the data is this guy, so of product over all alpha arrow in the original quiver of matrices of size ni and j cross matrices of size nj and I. And it's a subvariety because we have this constraint. Okay, so it's some affine variety. So just a very simple example. Take G to be SL3. So Q is just this guy. Then take beta to be alpha 1 plus alpha 2. So then we're just considering the representations where here we put C and C, and we have two linear maps. Call these linear maps X and Y. So then X of beta will be the variety of XY in C2 such that X times Y is 0. So notice that it's, in this case, the variety is reducible, and in general, there'll be a bunch of irreducible components to our variety X of beta. That's what we're interested in, the irreducible components of X of beta. So, state proposition, I guess, due to Lustig. All of these definitions are due to Lustig, I believe. Well, not all, but well, what I'm going to say now is due to Lustig. Okay, so the number of components of irreducible components of the variety X beta is the same as the number of isomorphism classes of modules for our original quiver, path algebra of our original quiver of dimension beta. That's the same as the number of ways to write beta as a sum of positive roots. And that's, well, this function is called sometimes the constant partition function of beta. It occurs often in representation theory. One way it occurs is as you take G to be a group integrating little g, B, a Borel subgroup, and N, the unipotent radical. And then this number is the same as you take the ring of functions on N, which is a module for the torus, and take the beta weight space of that. So this is the beta weight space of this as a module for our torus. Okay, why do all these equalities hold? Let me just give you a quick explanation. So to see this one, this uses that X of beta is the union of conormal bundles to the product of the GLVI orbits. The product of the GLVI orbits on the, I don't have a notation for it, but on the variety of modules for the path algebra of the original. So one could consider analogous construction for just the original quiver. Well, then you wouldn't have this guy and you wouldn't have this guy. And the orbits of this group acting on that variety, those would be exactly the same thing as the isomorphism classes of such modules. I don't know why that's the word modules. And this guy is exactly the union of the conormal bundles, so those orbits. So each irreducible component is the closure of a conormal bundle. So the number of irreducible components is the same as the number of orbits, which is the same as the number of isomorphism classes. This equality follows from the fact that the indecomposable CQ modules correspond to positive roots, and that's by Ringle's theorem. So indecomposable CQ modules. Oh, Gabriel's theorem, sorry. Positive roots. And, well, this one is well known. Okay. So this suggests so we're going to be studying later soon these components in more detail. But this suggests the kind of representation theory interpretation of these components. And in fact, we have the following theorem of Lustig, which says there exists an algebra structure. Well, this is some version of his theorem on, say, the vector space with basis given by all these components, such that this algebra is isomorphic to the algebra functions on this unipotent radical of our Borel, and the resulting basis is called, so we get a basis for this now given by the components because you have such an isomorphism, called the dual canonical basis, dual semi-canonical basis. So actually what Lustig did was something a little bit different. He considered a certain, well, in fact, Hopf algebra of constructible functions on these varieties. And then this is actually kind of taking the vector space given by the components is kind of taking dual to this space of constructible functions. The idea of, well, this idea of thinking about this dual picture, I mean, probably it's not due to them exactly, but I sort of learned of it from the work of Geis, Leclerc, and Schur. So they've constructed, they study this, and they've constructed, so this is quite old work. I mean, going back to the early 90s. This is much more recent work from a couple of years ago. So they've constructed a cluster algebra structure on this guy. And using the representation theory of this pre-projective algebra. And under this cluster algebra structure, the cluster monomials form a subset of this set of all components. So our one of the reasons why we sort of started looking at this was somehow motivated by, well, because this kind of brought these components to our attention, or at least my attention, anyway. I should also say that this work probably wouldn't have been possible without a lot of discussions with Bernard Leclerc. Cool. Okay, now on to so those are the components which we want to study. Now on to MV polytopes. So what's MV polytope? So it's a certain combinatorial object. Let me explain a bit. So let's take lambda will be our weight lattice. We can think of it as sitting inside of the real part of the Lie algebra of our maximal torus, which you could just take to be the result of tensoring this with R. It doesn't really matter, it'll play any role. And we have the Weyl group acting on our weight lattice. And we can consider Weyl polytopes, which are, you take some weight and you look at the Weyl orbit of that weight and you take its convex hull. So these polytopes are extremely familiar from representation theory because they capture, I mean, if lambda is the highest weight of the representation, then all weights of the representation live inside such a polytope. So here would be our lambda, so this would be V is SL3, W is S3. And the hyperplanes to these polytopes are given by Weyl orbits of fundamental weights. So one can rewrite this polytope in terms of these hyperplanes in the following way. You can say it's a set of all x in this CR such that x w omega I is smaller than lambda omega I for all I. So here, these omega i's are the fundamental weights. And here, I'm like a little bit kind of simplifying the notation. I'm not working, I mean, you could work with the dual space, but I'm just working with the space. I guess this should be dual here. But I'm just working with, I mean, I could work with, maybe I should really work with fundamental co-weights here, because these things are in the weight lattice. But let me just simplify and just stick with weights, because we're in the simply laced case anyway. Maybe I should have said that. Somewhere at the beginning, we should have said this. Simply laced. Okay. So these are the fundamental weights. This is the action of the on the fundamental weights by this Weyl group. So this equation is basically telling you that the walls of such a Weyl polytope are given by these. So here in this case we'd have omega 1, omega 2. Here we'd have S2, omega 2. Here we would have S1 acting on omega 1 and so on. Okay? This dot I just mean the usual action, not the dot action. I just put a dot to, otherwise the notation gets confusing. So this set, gamma, the union over of the Weyl orbits of the fundamental weights is called the set of chamber weights. Okay. Now we will consider other polytopes that have the same, that are defined by the same hyperplanes. So, given any collection of integers labeled one for each fundamental co-weight, one for each chamber weight, then consider the resulting polytope P of M dot, which will be defined to be X in this TR dual, such that X gamma is less than or equal to M gamma for all gamma, capital gamma. So this is a polytope defined by taking these hyperplanes and translating them however you like. Yeah? So the walls of any such polytope will be the same as the walls, parallel to the walls of the sky. So it could look like something wonky. I don't know. Something like this. Yeah. Yeah, you're even allowed to lose a bit of this. So it could even look like this. I did lose a piece here. You're good. So it could look like this. So I call such a thing a pseudo-biopolytope. Maybe other people have different names for this thing. Maybe better ones. And now I would like to explain what an MV polytope is. So let's start with SL3 MV polytopes. So an SL3 MV polytope is a pseudo-biopolytope where the following equality holds. So let me redraw my pseudo-biopolytope a little. I'll make it more regular looking. Like this. So where I'm going to introduce A to be this distance, B to be this distance, C to be this distance. So where A is equal to the max of B and C. That's the criteria. So A means the distance between the opposite faces here, B between this pair and this pair. In case you think there's something funny going on and that A, B, and C are playing not quite symmetric roles, it's not so surprising because, we're in the weight lattice, so there is a highest and lowest vertex. So A is the distance between the two faces which don't meet the highest and lowest vertex. And now we can define MV polytope for arbitrary simple simply based Lie algebra in the following way. So G MV polytope is a pseudo-biopolytope such that every two-face. So in general, think of this polytope as going to be some high-dimensional thing. It's going to have a bunch of two-dimensional faces. Maybe the most interesting case to visualize is the case of SL4, where you might have seen it. A picture of it once upon a time has a bunch of hexagons and a bunch of squares as its faces. I wish I could draw one for you. Once upon a time, probably could have, but I'm a little bit lost in my skill at drawing them. Okay, such that every two-face is either an SL3 MV polytope, so it satisfies this A equals max BC criteria over there, which you can think of as basically means you took this guy and you either stretched it out this way or you stretched it out this way. That's what you need to do to preserve this criteria. All the two faces will either be hexagons or rectangles. So if they're hexagons, you demand they're SL3 MV polytopes, or if they're rectangles, you demand nothing. Or an SL2 cross SL2 could say MV polytope, which is just any rectangle. Okay. So that completely tells you what the MV polytopes are in some kind of geometric way. Let me give us a little bit different take on them now. So alternatively, P, a polytope which is coming from one of those collections of integers, is an MV polytope if and only if the collection M dot, so these two things mean the same thing, is Bernstein-Zelevinsky data. Bernstein-Zelevinsky data means that two things. One, that some tropical flicker relations hold. So this tropical flicker relations is basically taking this A equals max BC and rewriting it in terms of the positions of the hyperplanes. So it looks kind of similar. It's something equals max of two other things. And second condition for being a Bernstein-Zelinsky datum is some length inequalities, which is not very important. It just means that these things actually are you didn't like push the one wall way too far away so that you didn't get any polytope at all. So it's something minor. Okay. So is a MV polytope if and only if. So we can speak about MV polytopes, or we can speak about these BZ data. Okay. So then we can talk about the weighted MV polytope. Weight MV polytope is the difference between its highest and lowest weights. And then we have the following proposition. I'll stay here. Which is that not stay here. Sorry. Before the proposition, let MV beta be the set of all MV polytopes of weight beta, but modulo translation. So if I translation by elements of the weight lattice. So if I take my MV polytope and I translate it around by the weight lattice, well, all these criteria will still be preserved, so it will still be MV polytope. So I mean, this set would be infinite otherwise. So let me mod out by translation. So two guys will be say equivalent if they're related by a translation.
What is highest and lowest weights? Just vertices?
Vertices, yeah. I mean, the vertices are all, yeah, the difference between the highest and lowest vertices. Thanks. Which you could write in terms of the Bernstein-Zelinsky data, if you like. Now, we have the following fact analogous to this fact, which is that the number of MV polytopes of weight beta, well, modulo this translation. All right, so this weight will always be, by the way, and it's not completely obvious, but this weight is always in our set lambda pos. It always is a positive combination of positive roots. The weight is always. So the cardinality of this set is actually the same thing as this constant partition function of beta. I mean, number of ways. As a sum. Positive roots. Okay, let me explain. Figure out time to explain the reason for this fact, which is kind of cute. Well, it's sort of cute, but maybe if you know a little bit about the subject, it's sort of obvious. Well, if you know maybe a lot about the subject, it's obvious. So there's the following reason. So how would you make? So this says that each time you write beta as a sum of positive roots, you should be able to make one of these MV polytopes. So the way you do it is like this. So let's fix. So this is the sort of outline of the proof. So you fix. Okay, so let's write. Let's fix a longest word. So write W naught is a product SI1, SIM, the Weyl group. And that gives me the vertices of these MV polytopes are naturally labeled by the Weyl group. So this longest word gives me a path from the, say, highest vertex to the lowest vertex, which will be labeled by W0. A path which goes along the outside of the polytope. I mean, along the one skeleton of the polytope. And then associated to this longest word, I get a listing of positive roots. It goes like this. Alpha I1, SI1, alpha I2, SI1, SI2, alpha I3, and so on. And these are actually the directions that these edges point in. Okay, so these are all the positive roots occur once in this ordering. Let me call them betas. Okay. So if I write, if I write beta, some way of writing beta as a sum of positive roots. So let's say it's mi beta I. Let me label it j, because it's running from 1 to m, not over the index set I. M here is just the length of W0. So if I write beta in some way, then I can build one part of an MV polytope by making this first bit be of distance m1, this part be of distance m2, and so on. Wait, m is a terrible letter. Okay, I'll call it p. p2, and so on. And then this tropical Flicker relations basically tells me that gives a unique way of completing the rest of the thing to an MV polytope. So that's why you have this bijection equality. Okay, so that's the definition of MV polytopes. Now is the definition of the components of these loosely quiver varieties. So the main result which I want to present is a natural bijection between the two sets. So we have two sets of the same cardinality, the number of components, and this thing. So there's a natural. So this is with the art. So I can explain to you how this bijection goes. So remember with the bijection, two objects involved. One is the components of these, components of x beta. Maybe I call it x beta. This is components of some affine varieties and this set of polytopes. Or equivalently, which will be useful, equivalently the set of Berenstein-Zelvinsky datum, these lists of integers. Let me explain how this bijection arises.
Kind of have it already.
Yeah, that's what I meant by saying that there was an indirect route. But we're going to make a direct route, namely not involving the choice of longest reduced decomposition. Okay, so for each chamber weight, which will be some Weyl orbit of a fundamental weight, there is a unique A of Q module, unique up isomorphism, A of Q module, with, we call it W of gamma, with dimension vector given by omega I minus gamma, and Sockle, that means the maximal semi-simple submodule, SI, where SI means the A of Q module, which is just C, a one-dimensional vector space in the I spot and 0 elsewhere. Let me show this in an example. It's probably the easiest way to understand this statement. So example is to take Q V is from before, this guy. Take gamma to be the violet orbit acting on the second. So we're in the G is SL4. Longest element acting on the second fundamental weight. And if you check, you'll see that omega 2 minus gamma, what the dimension vector should be is alpha 1 plus 2 alpha 2 plus alpha 3. So my module W gamma will have a two-dimensional thing in this second vertex, and one-dimensional things in the first and third vertex, and we'll have socle SI. So there's a unique way of doing that. It'll look like this. And so when I draw this kind of picture, it's a kind of picture of a EFQ module. I put a dot for each basis vector. So you see two bases, and the position of the dots tell you which vertex the basis vectors are at. So you have two-dimensional. This will be a basis for my V2. This is the V1. This is the V3. And these arrows are telling you how these arrows and the ones pointing backwards are acting on those basis vectors. And there's some constraint forced by like this composition. It actually has to equal this composition. That's fine. So the socle is here. This is the maximal semi-simple submodule of this module. And it's just one dimension in the second slide. Okay. So using these special modules, I'm gonna construct my bijection. So define function d gamma from my x beta to integers by v goes to dimension of the Hom space from w gamma to v. So any point in x beta is a AFQ module. So I can look at the Hom space as AFQ modules between these special modules and my module V. And I can take the dimension of that Hom space, and there will be some function, constructible function on this affine variety x beta. So these are constructible functions on this algebraic variety. So they are constant on the dense part of each component. Of x beta. And so we can speak of, for each, so they're constant on a dense part of each component. So for each component, we can speak of the value of the function on that component to be its value on this dense part of each component. So this sort of theorem, so let me say that word. So we call it the generic value. So we have a generic value for each function on each component. X beta. So the theorem for each component, the generic values d gamma v, gamma and gamma. So v will be a kind of this. So this will be this generic value on a component. For each component, this thing is. So this is a collection of integers, positive integers, one for each for each chamber weight. And so the statement is this is a BZ datum. And the second part is this is a different collection of integers for each component. So this gives a bijection as desired. And from the components of x beta to mv beta. So I previously mentioned that there was also bijection between MV polytopes and well, something to do with Mirkovich-Valonin basis, which is related to Mirkovich-Valonin cycles, some subvarieties of affine Grassmannians. And that bijection, which I constructed in my thesis, is defined in almost identical fashion. There's some constructible functions on some thing which contains all the components, and its generic values on the components is BZ datum. So I like this result because it sort of improves the parallelism between the two pictures. Now let me explain some further directions and conjectures that we can make given this result. Direction. So the first point concerns multiplication in the dual semicanonical basis. So let A and B be components in some in one of these, in some of these varieties, say x beta prime. So then they give, under this isomorphism Lustig, they give vectors or elements. Let me call it little VA, little VB in the ring of functions. And we can compute the product in this ring and expand it. So expand it in terms of the element. So this will be a sum over C, some components of, so C will range in the components, I guess, of the variety x beta plus beta prime. And we'll get some coefficients. I'm not too concerned with these coefficients. More I'm just concerned with whether they're 0 or not for some coefficients. Now the conjecture that we would like to use this theorem to prove is that this NA beta C is 0 unless the MV polytope, so let me call it P sub C, so this would be the MV polytope corresponding to the component C under that bijection. C is contained inside the Minkowski sum of the MV polytopes for A and the MV polytopes for B. Equivalently, because of the bijection, this is saying that the generic value of d gamma on the component PC is smaller than or equal to d gamma on PA plus d gamma on PB. So let me mention two kind of pieces of evidence or interesting things related to this conjecture. So sometimes AB is equal to some vector. Sometimes VA times VB is outright equal to VC for some component C. In this case, so, well, what if and only? So this occurs if it's a slightly confusing statement, but if the component C is made up of modules which are direct sums of the modules in A and B. or the closure of such modules. Yeah? So this was proven by Geist, Leclerc, and Shor. And in this setting, well, it's clear that if this occurs, this implies that the polytope for C, well, this implies that these d gamma, sorry, I guess this is not supposed to be a PC. So this implies that d gamma, generic value on the component C, which would be the value on the direct sum, so the dimensions of Hom spaces they'll add under direct sum, you'll get this. So this is C is the Minkowski sum of NB. So when, I think this is actually if and only if, when C is made, when this component C is made up of direct sums and modules from the components A and B, then the polytope for C will be the direct sum, the Minkowski sum of the polytope for A and the polytope for B, because the dimensions of the Hom spaces will add. The second remark is that a version of this conjecture for the MV basis was formulated by Jared Anderson in 2001, and a proof of the conjecture will hopefully appear in work, another paper with Pierre Ballmer. So I believe we know how to prove this conjecture in the MV case. So if we have the conjecture in the MV case and we had it in this case, it would add sort of more of a link between the two bases. Now the final point of further direction I want to make is that the quiver variety picture works in the Katz-Moody setting as well. So this is unlike the affine-Grassmannian constructions. Although, well, there has been some recent work in this direction, but let's say for now that it doesn't work, at least not nearly as easily, in the Katz-Moody settings. So, but whereas the quiver variety picture goes through, so one can try to produce these BZ datum for Katz-Moody Lie algebras by the same construction. So one can use this. This, I mean, our work to produce BZ data in the Katz-Moody, in particular affine as well, case as well. BZ data / MB polytopes. But this is sort of this theorem is not obvious. I mean, the proof of this theorem actually does use the finiteness. The fact we're in a finite dimensional Lie algebra. We're in the finite type, but probably one can do something that will go through in the Katz-Moody case. I'll stop
there. Questions or comments?
So, this work by Geist, Leclerc, and Schroer, they associate, I guess, the more or less representation of the pre-projective algebra directly some polynomials on end, right?
Yeah.
So that this same gamma will correspond to generalized minus functions. But I forgot, it's not the same representation they use for this purpose.
Yeah.
The W gamma.
Yeah, I think it is the same. You mean under their description of these gammas, did the W gammas go over to the generalized minors? Is that the question? Or?
Yes. There is some kind of strange duality between ordinary, I don't know, flag varieties and these tropical ones, right? The gammas. And I never was able to understand how they interact, but here it kind of seems to be maybe.
I'm not sure what that's. I'm not sure. I'm not sure of what the relationship between this and whether these do go to the
But
general.
they consider the same representation. You have to take this generalized minus that are elements of this dual canonical and dual semi-canonical.
Yeah.
So they should correspond to
Yeah, I
models
think.
of-
Yeah, I guess they probably should. Yeah.
It's good. How to, is there a way to move from a simple list to a non-simple list, like some kind of folding, because there is always the same kind of problem everywhere.
I'm not sure. I didn't really think about it very much. Probably, but I don't know. No, I don't know.
So in this setting, and in the fine Grassmannian setting is also.
No, well, in that fine Grassmannian setting, there's no problem. I mean, you can deal with non-simple list groups without any trouble.
So there is absolutely
I mean, I
no
know-
difference.
Yeah. Well, the only difference, well, you probably know, the only difference is the when you define them. Well, say when you define this MV. I mean, in the geometry, there's no difference. When you define MV polytope, well, you know there'll be a difference. You need a condition for each rank 2 group. You have a different condition depending
Right,
on the thing. But in the geometry, there's no problem in that case. Here, I don't know what the geometry. I mean, maybe, I'm sure people have thought about it, but I'm not really an expert.
So if you have it, sometimes this more direct connection, then probably it will be something.
Yeah, maybe. Yeah, maybe. Yeah.
Any other questions or comments? So let's thank Joel again.